This is the sixth and final section of the Conic sections 2 chapter, and this is on loci. Now before we get into the method we're going to use for loci, I've just got here this table which is from the formula booklet, so you can see what you're given. So these two columns here, do one of these curly brackets, terrible curly bracket. This is from the Conic sections 1, so this is what you did in AS. And then these last, or the first column here, the ellipse and the rectangular hyperbola from Conic sections 2. So this is your A-level content. Now you'll see what you haven't got in those tables is the general form for a tangent or a normal for any of these. So I'm just going to pause this and list them, go through them quickly, and then go through the method for loci. So you can see now over here, these are all the results for the tangents and normals for ellipse, parabola, hyperbola, rectangular hyperbola. So as I said before, these are not in the formula book. So it's useful to memorize these results because then you can quote them directly, unless a question says, can you prove that the tangent is a particular result or the normal is a particular result? Otherwise, you can just quote them directly. So for example, if we're doing one of these loci questions, we can quote it directly. Now, I've drawn what these different graphs look like at the bottom here. Now, if we're trying to answer one of these loci type questions, normally it's to do with, let's say for example, we've got, and I'll try and draw a little sketch down here, an ellipse, for example. This is an example type thing, and let's say we've got tangents to this ellipse. Let's say you've got a tangent there and a tangent here, and those tangents cross at a point, and let's say that we call this point R, for example. What we're interested in is, as these tangents move around, what is the loci of this point? Or it may be, for example, that we have sort of tangent like this, and we're looking at maybe a point which is a quarter of the way along this tangent, for example, or halfway along, and we're looking at the loci of this point. So as this tangent moves around, or it could be tangents or normals, as these tangents or normals move around the shape, let's say the ellipse or the parabola or the hyperbola, as they move around, what path do they trace? What's the locus of the of those points? So quite often what we do when we do these questions, we would find out what the general point is, let's say R. So find R. Yeah, I'm just called it R. It could be called anything in the question. And we'll find its general coordinate. And what we would do, we would call its general coordinate large X, large Y, capital X, capital Y. And we can express the loci in terms of X and Y. Yeah, so use a capital X and capital Y to describe this general point that we want to find the loci of. And then once we've done that, we need to express that loci in terms of X and Y. Express loci in terms of this large X and large Y. And that's the general method we take to work out the loci, the path of a certain set of points. Okay, so the tangent to the ellipse with this equation here, so it's just a general ellipse here, nothing special about it, not given the values of A and B, at the point P. So there's a tangent at this point. It crosses the x-axis at A and the y-axis at B. Okay, so it crosses the coordinate axis, both the coordinate axes. Find an equation for the locus of the midpoint of AB as P moves around the ellipse. So as usual, I'm going to start with a sketch of what this looks like. Now, just because it's a sketch, this doesn't mean this is what it's going to look. It's going to look exactly like this. Okay. So there's my fantastic ellipse there, and then I've got this tangent, and it's let's try and draw a tangent here. So a tangent like that, and it's crossing the x-axis at A. So this is point A here, and this is point B, and it's a tangent at the point P here, and P has coordinates A cos t, B sine t, and we want to find the locus of the midpoint of AB as P moves around the ellipse. So basically, as this point P here, as where the tangent touches the ellipse, as that moves around, we want to know what is the locus of the midpoint. So let's call this point here, this is going to be the midpoint of AB. Now we may not be able to visualize what that locus is, but we'll be able to express it algebraically. So as this tangent moves around, we might be able to imagine that. So this tangent swinging around the ellipse like this, what happens to this midpoint? And these types of questions are really good to explore using things like GeoGebra, where you can actually find somebody that's already done one like this, or you could even make one yourself and put some sliders in, and as that moves around, see what happens to the midpoint. So at this point, we can actually just quote the result for the equation of a tangent to an ellipse. If you need to go back to that first slide and have a look, and that would be so the equation of the tangent. So we don't need to prove this. If we've remembered it, we can just quote it. If you can't remember it, then you would just use this general point AB here to put into y minus y1 equals x minus x1, and m you would get by differentiating this, and or you could take the parametric form and differentiate the parametric form, or use implicit differentiation to differentiate this. So it'll be a couple more steps, differentiating this or differentiating the parametric form, and then using y minus y1 equals m x minus x1, and you'll get this equation of the tangent. But if you remember it, it's even better, because you can just quote the result as a y sine t plus bx cos t equals AB. Now we're told that the tangent crosses the axis at the points A and B. So if we start at the point A, or at the point A where it crosses the x-axis, we know that y equals 0. So what we'll do, we'll put y equals 0 into the equation of the tangent. So that means all of the first bit is gone. Actually, let me write it out. So a times 0 times sine t plus bx cos t equals AB. So from that, we will get just bx cos t equals AB. Now we want what the x coordinate is. So that will give us, well, we can divide both sides by b. That will cancel out. And that will give us x equals a over cos t. So this is the point where the tangent crosses the x-axis. So the actual coordinate of a is a over cos t 0. Or you could say, instead of a over cos t, you could write instead a, let's see, sec t, couldn't you, instead, because 1 over cos is sec, so you could write that instead. So we'll now look at B. So at B, where it crosses the y-axis, x is 0. So we'll put x is 0 into our equation of the tangent. So we'll have ay sine t plus b times 0 times cos t equals ab. So from there we will get ay equals sine t, sorry, ay sine t equals ab, ay sine t equals ab. Here our a's will cancel out. That will leave us with y sine t equals b, so y will equal b over sine t. So the coordinate of point B will be 0, b over sine t. Now, just like we wrote a over cos t, we could write as a sec t. We could write this instead as b cosec t, because 1 over sine is cosec, so we could write that instead. Now the next thing that we want is the midpoint of AB, midpoint of AB. Okay, so since we've got the coordinates of A and B, and the other coordinates are just 0, it's just going to be half of the x coordinate, half of the y coordinate. So A over 2 cos t will be the midpoint of the x coordinates, and the midpoint of the y coordinates, again since one of them is 0, will just be over 2 sine t. So that's our midpoint. And what we want to do, as I said, the method is to write these points in terms of capital X and capital Y. So we're going to let capital X equal A over 2 cos t, and capital Y equal b over 2 sine t, because we want to write an equation that shows what x and y are doing, because this midpoint is basically, let's write this down, we've just called it xy, and we want to write down an equation that tells us, well, what is that coordinate xy doing as p moves around, as that point where the tangent touching, as that point where the tangent touches the ellipse, as that moves around the ellipse, what is this general point, capital X, capital Y, doing? That will be the locus of the midpoint of AB, this coordinate that we've called capital X, capital Y. So let's put my 2 in that I missed out here. Now what we need is an equation that allows us to put x and y together into a single equation. Now, since I've got cos down here and I've got sine down here, the equation that I should be thinking of that is going to link these two together is going to be sine squared plus cos squared. Maybe a different equation in a different case, but that I can use to link these two equations together, and probably at the same time eliminate t. So first thing we're going to do is to write these or this coordinate in terms of cos t and sine t. So if I start with the first one, I'll have cos t is equal to a over 2x. Yeah, if you rearrange it, that's what you'll get. Cos t equals a over 2x, divide both sides by x, times by side by cos t. And then if I do the same with sine t and write sine t as the subject, I'll get sine t equals b over 2y. Now I've written them like that, I can join them together. So I can say something like, using sine squared t plus cos squared t is 1. I can now write an equation that tells me what the locus of this midpoint is. So sine squared will be b over 2y all squared, plus cos squared, which will be b over 2x all squared, equals 1. So this here, this is the equation of the locus of the midpoint of AB as P moves around the ellipse. And it seems like I need to learn my alphabet because that B should be an A. Okay, so here we've got a normal at P and another normal at Q to a parabola with just general equation y squared equals 4ac, and these two normals meet at the point R. We need to find the coordinates of R. We need to show that P, the product of P and Q is -1, and then there's something about a locus in part C. So we're going to try and draw a sketch. Yeah, now sketch isn't sort of compulsory, but in terms of practicing questions, you may not have time to do it in the exam, but in terms of practicing questions, it's useful to do. So we've got this parabola here, so we'll just sketch out that parabola. So we've also got a focus, and let's put focus in here because I think that's in part B, 8, 0, and we'll have our directrix here, which will have equation x plus a equals 0. And then we've got these two normals and they cross at the point A. Now remember, this is only a sketch, so I don't expect this to be exact. So let's say we've got a normal here, okay, and let's say we've got a normal here, like this, yeah, and the normal, this point here is P, and this has coordinates A, P, Q to A, P, and this point here has coordinates A, Q, P, so basically the same thing but with Q's in it, A to Q. So you've got to be really careful in the algebra because you might easily get a P and a Q mixed up. And this is the point R where they cross, and the equation of this parabola is y squared equals 4ax. So just like in a previous example, we're going to quote directly the result for the normal to a parabola. Again, you could prove it from scratch, but it will probably save you a couple of minutes in the exam if you could memorize it. So we'll just write down equation of a normal to a parabola. So again, you can always go back to the first slide and remind yourself of it. And that's going to be y plus tx equals 2at plus at cubed. Now this is the equation of a normal that passes through the point at squared to at. So we need to compare that with the coordinates we've been given. Now if we have a look, so you've got to take care, you wouldn't just replace x with ap squared and you wouldn't replace y with 2ap. That would be incorrect because the coordinate is of this form at squared. So you can see the only difference is at point P, where I've got t, there's p instead, and at point Q, instead of where I have t here, I've got q. So at point P, so the normal at P The only difference it's going to have is in this general equation of the normal, I just replace the t with the letter p. So y plus px equals 2ap plus ap cubed, and the normal at q is going to be y plus qx equals 2aq plus aq cubed. Now we want to find the intersection of these normals. That's the point R. So that means solving simultaneously. Okay, so let's write down R is the intersection, I think it says it in the question anyway, of these two normals, So that means we need to solve simultaneously. So now I think what we can do, let's just subtract these two equations. Let's do the top one minus the bottom one. That will eliminate y. So if I just put here that we're subtracting, and then write the result down here. So y minus y is nothing. Then we'll have px minus pq, or qx equals 2ap minus 2aq plus ap cubed minus aq cubed. Now straight away I can see that I can factorize because I want to find out what the x coordinate is. So I've got x equals, or x and then p minus q. Then on the other side I can factorize 2a and p minus q, and then I can also factorize a and p cubed minus q cubed. So x will equal both sides divided by p minus q plus a p cubed minus q cubed over p minus q. Now it would be so nice if I could divide everything by p minus q because it's a factor there, but the problem is this. Now there is a way of factorizing it, and you know, it's not something that's in the formula book, but if you can remember this factorization of this, that will be useful. Now I'm just going to write the factorization at the top. So factorization of, let's call it anything cubed plus or minus, it could be minus something else cubed. So this will give you a plus or minus, so you'll have the same sign as you've got in the bracket at the beginning here in the first bracket. Then in the second bracket you'll get a squared. Now here you'll get the opposite sign to what's in the very first bracket, so it's minus plus, and then ab, and then it's always plus b squared. And this is going to help us to factorize what we've got at the bottom here. So if we go back to the question now, we can write that the second bracket, so now we're going to factorize, so right, x equals, we've got the 2a p minus q, and then a, and then the p cubed minus q cubed will factorize to give you p minus q, yeah, following what's in red at the top and highlighted, then p squared. Now this side's going to be the opposite, so plus pq, and then plus q squared, all over pq, or p minus q. Now what that allows us to do now is to cancel this all out. So that and that will all cancel out. It just gives it a nicer form, and it makes the algebra then for finding the y coordinate a little bit easier. So the x coordinate is going to be equal to 2a plus a times by p squared plus pq plus q squared. So knowing that factorization is useful. So now we want to find the y coordinate, which basically means substituting that value of x into our equation. So I'm going to use this normal here. I could use that one or I could use this one, it doesn't matter. I'm going to use the first one. So I'm just going to rearrange it. So I've got y equals 2ap plus ap cubed. So I'm just taking away the px from both sides. So this x here I'll replace with this here. So that is going to get substituted into, so let's put like a box around here to show you that I'm now substituting that into here. Let's see what we get once we do that. So I'll have y equals 2ap plus ap cubed minus p times by x, which is all of this, 2a plus a. Now if I didn't have that factorization, what I'd be substituting for q would be a lot more complicated than what I've got written here. So I should be able to simplify this actually without having to, without having to expand it all out. Actually, I think I might just expand it all out just to make sure. Plus ap cubed, and then I'll have minus 2ap, so that's going to be gone because the first term is the same as that, and then I will have ap squared times by minus p, so minus ap cubed. Okay, so that cancels out the other ap cubed. Then I'll have apq times by minus p, so minus ap squared q. Then the last term will be aq squared, so it'll be minus a p q squared. Now what will happen is these will cancel out like that, and with what I've got left here for y, I can factorize that, those last two terms. I can take out minus apq, and then in brackets I'll just be left with p plus q. Right, so that leaves my final coordinate. R will equal my x coordinate, which is this, 2a plus a p squared plus pq plus q squared, comma my y coordinate, which is minus apq and then p plus q. Okay, so let's move on to part B. The chord PQ passes through the focus A0 of the parabola. Now, if you refer back to my sketch, you can see why it's just a sketch, because if I drew a chord to PQ, it's not passing through the focus. Yeah, so maybe I will just change my sketch so that the chord is passing through the focus. So let's change this a bit and see if we can, what I might do is draw the chord in first and then do my two or draw a line that's going through the focus first and then maybe turn that into a chord. So maybe something like this. Okay, the chord PQ. So now I've just changed my sketch a bit so it fits the question, and I'll put the coordinates back in again because they haven't changed. We've just moved from a normal to a chord. So let's put this in. this. Right, so now we've got that diagram there. The first thing we're going to do is to find the equation of this chord PQ. So we're going to find, first of all, the gradient of PQ. Now we've got points that it passes through, so we can use these 2 points here. We can use P and Q. We could actually use P and the focus here to find the gradient, or the focus and Q. So any one of those pairs, since it passes through that point, we can use any of those to find a gradient. Now I'm going to use the points P and Q to find a gradient. So I want the change in y over the change in x. So I'm going to do the y coordinate of P, 2AP, minus the y coordinate of Q, so 2AQ, over the x coordinate of P, AP squared, minus the x coordinate of Q, so AQ squared. So we're going to do what we can do to simplify this and factorize it. So I can factorize the top, I'll factorize the bottom. Now the bottom is just the difference of 2 squares there. So I'll have 2a p minus q over a times by p minus q, p plus q. So by factoring it out like that, I can see that the a will cancel out, the p minus q will cancel out. So this gives the gradient of pq as 2 over p plus q. So now I'm going to use y minus y1 equals mx minus x1, and I'm going to use the focus as x1, y1. So I'm going to use the point a0. Now again, I could use any point for x1 and y1, just like I could use any pair of these 3 points here for the gradient. So I'm going to use this point as a point that it passes through, put that into x1 and y1 to get the equation of this chord. Now I could do exactly the same by putting this point P as x1, y1, or this point Q as x1, y1. So it doesn't make any difference because it passes through all 3 points. We can use any one. So y minus y1, so that's going to be y minus 0, equals m, so 2 over p plus q, equals m. Now my no, I've done my m, m and then x minus x1, so x1 is a. Okay, so this is the equation of the chord PQ, this bit here. Okay, now that chord passes through 3 different points, doesn't it? So I could use substituting now any one of these 3 points again into this equation of this chord, and then I should get an expression for P and Q, and I should get that this PQ equals -1. Now, as I said, you can use any one, so I'm going to put in the point Q. So I'm going to put in the point AQ squared 2AQ. So any one of those 3 points will do. Right, so if I do that, let's see what I get. So I will have y, now y is 2AQ, equals m, so 2 over p plus q, times by x, so it's going to be AQ squared minus a. Okay, so substitute that in. I'll multiply out the brackets, so I will get 2AQ equals 2AQ squared over p plus q. Oh, actually, I can write the whole thing over that. So minus a all over p plus q. We'll multiply both sides by p plus q. I'm going to have to make some space at the top in a moment. So that will be 2AQ times by p plus q equals 2aq squared minus a. Now I can divide everything through by a, because a is a factor there. So that will give me 2q, and we'll expand the brackets as well. So that will be 2pq plus 2q squared equals 2q squared minus 1. Now I'm going to pause it a minute and make some space at the top to finish off this question. Okay, so I've got a bit of space. Now before I continue, I've had a look at my working here, down here. Now I should have multiplied this by 2. So this at the top here, you're probably panicking, wondering why is that not there? That should say 2a. So that's changed. Let me just highlight that. Now if that has changed, what that means is this would have said 2a as well. So there would have been a 2 here, which means that not only would the a's have cancelled out, that 2 would have cancelled out as well. So these 2's go here, here, and here. So now I've corrected that silly error of mine. This is where we would have got to pq plus q squared equals q squared minus 1. So then we can take away q squared from both sides. So then we'll end up with pq equals -1 as required. Now part C, last part of this question, show that the locus of R is a parabola with this equation here. Now remember, the way to deal with the loci part of the question is to write the points that you want to find the loci of as capital X and capital Y. So we're trying to find a loci of this, p squared plus pq plus q squared. So big X equals that, and big Y, capital Y, equals the other point, which was negative apq p plus q. Basically what we need to do is to put these two together into a single equation. Now we've been given some information that in the previous part, p times q, the product of p and q, is -1. So we can use that to simplify what we've written. So the x coordinate will become 2a plus a, and then we'll have pq, or p squared, minus 1, because p times q is -1, plus q squared. And we'll simplify that in a moment. And for y, again, where the pq equals -1, you'll have a p plus q. So if I take the first one and simplify the x, so now I'll have 2a. Now if I multiply this out, actually I'm only going to multiply part of it out, so I'll have plus a p squared plus q squared, and then the a times by the -1 will give me -a. So I've got my x coordinate as equal to, so 2a minus a is going to be a. So let's just put x equals a plus a times by p squared plus q squared. Now we need to put these two equations together. If I look at what I've got written for y, if I square this, I can probably get p squared and q squared with some other stuff, but then that will allow me to substitute what I have for x into here. So I'm actually going to rearrange this x a bit further so that I've now got something in terms of p squared and q squared. So I'll have p squared plus q squared, okay, which will allow me to substitute it into the y squared when I square it in a moment. What will that give me? So I'll have x minus a over a. So this is, I've written it correctly, this is what I'm going to use to substitute when I square my y part. So if I square what I have for y, so y squared is going to be a squared, and then p plus q all squared, which I know is going to give me y squared equals a squared, and then I'll have p squared plus q squared plus 2pq. Now I know that the pq is -1, so I've got y squared equals, now what I can do is take that out, so p squared plus q squared, and then because this is -1, I'll have -2, so I'll have -2 times by a squared, so I'll have minus 2a squared here. That's what it becomes. So now I can make my substitution, and I make my substitution here, so I can replace that with this. Yeah, so I need some way of putting the x and y parts together, and this is the way to do it. So now I have y squared equals a squared times by p squared plus q squared, which is x minus a over a minus 2a squared. Now I could leave it like that, but this can be simplified a bit. So this a and that squared will cancel out. So that will just leave me y squared equals a times by x minus a minus 2a squared. If I multiply that out, I'll have ax minus x squared minus 2a squared, which is ax minus 3a squared, and I could factorize it again and write y squared equals a and then x minus 3a. Okay, so these last few steps that I did here to simplify it are necessary because that's the form that they wanted. Yeah, we need to get it into this form here. So yeah, just going through this again, we take the point that we want to find a locus of, and we write capital X equals the x coordinate, capital Y equals the y coordinate of what we want to find a loci of, and then we need some way of putting x and y together. Now in a previous example we used, I think, sine squared plus cos squared. With here, I mean, there are other ways of doing it. You could complete the square, for example, but with here, because we've got the p squared and q squared, I can get p squared and q squared from this if I expand the brackets, and then the rest is just algebraic to get it into this form. You should now be able to complete exercise 3F on pages 86 to 87. Now, whenever we do these loci questions, a quick recap here, we do them in all the same way. So let's say we want to find the loci of a point R. Let's call this point R. Now this point R might be the intersection of two tangents, the intersection of two normals, the midpoint between two axes of a tangent of a normal, or anything like that. But we'll call this point that we're trying to find the loci of R. Then we find the general coordinates of R. So find general coordinates, that'll be algebraic coordinate of R. Once we found the general coordinate of R, we'll write big X equal whatever the X coordinate of R equals, and Y equals the Y coordinate of what R equals. Then what we need to do, X and Y need to be put together to form a singular equation using X and Y, and sometimes that means eliminating T. It all depends on the equation. So the last step would be form a single equation involving X and Y, involving big X and Y. Now that may mean the use of a trig identity if you've got trig in there, but a single equation. So maybe Y equals something in terms of X, or Y squared, like the last example, equals something in terms of X. And that equation there will give us the loci of R.